Hello, this is Stukel here to do the lesson specifically on the rest of the sound unit, whatever that may be. We got a lot of disparate topics to talk about today, so let's get this started. We are going to get this started by talking about the concept of beats. You are all going to need to be on page 175. 175 in your math physics books. Hopefully you're all there, and let's get us started talking about this. So first things first, what is a beat? A beat is a interference pattern between two different sounds. Specifically, when you have two different sounds that are very similar to each other, when those sounds are in the same place, they will interfere with each other. They're in the same place at the same time. They create interference that is creating constructive or destructive interference, making sounds larger, more volume, or smaller, less volume. Let's take this as a brief example. We have two different frequencies. One frequency is one wave has twice the frequency of the other. So one frequency is twice as big as the other. Let's call that frequency 1. And let's call this lower frequency 2. Let's see what happens when we put those two frequencies together. You first have the compressions lining up with each other. A compression over a compression. This creates constructive interference. Let's put this in blue right here. Note how we have a compression and a compression there for constructive. We have a compression and a compression here, compression and a compression here, compression and compression here, so on and so forth. We can say all of these places have constructive interference with each other. They are increasing in volume. Let's take red, and let's call red our destructive interference. This is where we have, say, a compression and a rarefaction on the same place as each other. The compressed air from one wave matches with the uncompressed or rarefacted air from another wave, and those two things even out to just not compressed nor rarefacted. That would be a destructive interference. Here. Note how what this means is that we're going to have a pattern of destructive interference and constructive interference going on over and over and over for this wave. This means that the volume is slowly going to get higher, lower, lower as time goes on, just due to that interference pattern. This creates what we call a beat frequency, a frequency that is a result of the interference pattern of two other frequencies. Let's listen to what that sounds like. I'm going to flip us over here to my display capture. We're going to go over here to beat frequencies, and then we're going to flip the volumes. So you're all able to hear the whoa-ing of that sound. Let's test that just one more time. And now we can visualize that. We can actually go and look and see what that looks like in a sort of wave. We'll watch this next video. The next video is going to do something very similar to what this previous video did, but instead of using tuning forks, it'll use the wave generators similar to what we've used with the speakers, and it will set the waves very close to each other. I want you, while watching this video, to listen with your ears to the beats and hear what happens to the beats when the frequencies that the two things are producing are closer together versus what happens to the beats when the things' frequencies are far apart. Note how the further the two beats, or the further the two frequencies got from each other, the more frequent the beats were. When there was the 404 frequency and the 400 frequency, it was woo 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 woo, versus when it was the 400 and the 405 frequency, the woo 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 woo, right? That frequency becomes more pronounced, more frequent. This all comes into then the equation for this. We can come over here and we can look over here at this question. First things first, let's just briefly check up on this. We have a trumpet that's playing a note at this frequency, a clarinet playing a note at this frequency. We're asked how many beats are heard every minute. So the first thing we have to do is find that beat frequency. Our beat frequency is equal to the absolute value of frequency 1, or 2, I suppose, minus frequency 1. Note how these are the absolute values. It doesn't matter which number you subtract from another number in an absolute value, as they will give you the same answer in the end. So just keep that in mind. We have this here. This is our set up. We come over here and we're like, we know our first frequency is 320 minus 328. The absolute value of -8 then, which is equal to 8 hertz. Okay, so our beat frequency is 8 hertz. Let's recall what a hertz means. A hertz means that that's one beat every second. If that is one beat every second, oh, that's a horrible beat per second. Beat per second. There we go. So we have 8 beats every second. Well, if we're looking for how many beats are heard in a minute, if we hear 8 beats in 1 second, well, there are 60 seconds in a minute, so we should hear 8 beats per second times 60 seconds per minute. Seconds will cancel out. 8 times 60, we get a solid 480 beats per minute. So that's how many beats or the woo-woos we hear in a minute. Okay, we're all good with that. Now note, the equation for beat frequency isn't anything too crazy. We're doing subtraction with a little bit of absolute value, so nothing too crazy. Where this gets weird is where this absolute value comes in when we're looking for the frequency that is creating this beat. Looking at question number 2, we have a piano playing along with a tuning fork that gives us a beat frequency of 4 hertz. That is the frequency that we hear in this space. For the tuning fork is set at 400 hertz. If our, say, F1 is 400 hertz, then we're looking for the frequency of the piano. We know our beat frequency is equal to the absolute value of whatever the frequency of the piano is minus 400, or 440. Ooh, whoopsity. This is a 40 there. So we know that this is our frequency 2, frequency of the piano, minus 440. This absolute value we get as then the plussing minusing of the beat frequency. We can take our beat frequency. This right here is 4 hertz. So when we get rid of this absolute value, we get plus or minus 4 is equal to frequency 2 minus 440. When we add 440 to both sides, then we're either going to add 4 to it or subtract 4 to it. So we get 440 plus or minus 4 as equal to our frequency 2. And from there, we get our frequency 2 as either 444 or 436 hertz. One or the other. We can note we can do this in number line form as well. If we have 440 as our base frequency, hertz, then either by going 4 up from that or 4 down from that, we can get the two other frequencies we have, 444 hertz or 436 hertz. So just be aware there might be multiple answers to these problems. There's not necessarily a guarantee we can find the frequency that creates this. Your homework is going to provide some questions that, play around with this idea and force you to try and find a frequency in a space that we don't necessarily know where it is. Okay, so just keep that in mind. Let's flip over here to vibrating strings. Vibrating strings. There are 4 different variables that dictate the frequency of a vibrating string. We are going to have to do a little searching to figure out what these are. So I'm going to do a little bit of stuff off book for this. Let's take a look at where some of these things are. First things first, let's recall that the fundamental frequency of a string is whatever frequency is created by the string vibrating at a wavelength that is twice the length of that string. Frequency when lambda is equal to twice the length of that string. Okay, let's recall that for this frequency. We know, based on the wave equation, velocity is equal to f times lambda, that this length then will affect our frequency. Whatever our length is, that will change what our frequency is. Additionally, the velocity is going to change how our frequency works. So either changing this or this will change our frequency. Sorry, I'm recording a thing right now. So when we're doing this, you're going to be wanting to figure out a way to change the velocity. Let's recall, velocity is controlled solely by the medium the wave is traveling through. Whatever this string is, that string must control that velocity. How can we control the string? Well, we can change the thickness of the string. It can be thin or thick. This would be by changing the diameter of the string. If we have a cross section of string, looking at how far across that string is, the length that goes across that string there for its thickness or thinness. We can also think about whatever the string is made out of, the material of the string, and the material itself doesn't matter as much as the density of that material. So we're going to be using the density of the material, the mass per volume, right? Mass per volume of whatever material is creating the string. Okay, good with that? Good with that? And then finally, the last thing that really matters is the tension, the force of tension that is in the string, right? So however stretched the string is, whatever is pulling the string this way or this way. And this is something you could get from, say, anyone who plays a stringed instrument could tell you that these things can affect the frequency of, say, a violin string. If you want to tune your string up, you use the little knobs on the end of the scroll of the instrument and either up the tension or decrease the tension, depending on how you're going to want to change your frequency. You can change the material that the string is made of. Some strings are made of plastic, some strings are made out of metal. Depending on that material, you're going to get a different frequency out of your string. And then finally, the thickness of the string, right? If you want to have a lower frequency string, you use the larger strings. It's just how they end up working. Okay, so where does this all come in? This all comes in this. We know that our frequency is dependent on our velocity and our wavelength. Our wavelength is strictly dependent on the length of the string. Our velocity is equal to the square root of the tension through the string divided by the linear density of that string. The linear density of the string being equal to the actual density of the string times pi r squared, or instead of r, 1/2 diameter squared, like so. Okay. Still with me? You still don't have to write any of this in your book. This is just for the background behind this. This is all going somewhere. Trust me on this. All of this goes to one essential thing then, and that is that the frequency behind a string, the frequency that is necessary for a string to vibrate, can be delivered as 1 divided by the square root of pi times the square root of the tension divided by the length of the string times the diameter of the string times the square root of the density of the string. And I think this equation's horrible. It's disgusting and atrocious, and you all should too. We're not going to remember this equation. As is with all things, every equation is going to be given to you. We're not even going to give you this equation because it doesn't really matter. In the end of the day, this is just a way to demonstrate how each of the various things impact the frequency that a string creates. The more tension you have, the higher the frequency. The longer your string, the lower the frequency. The thicker your string, the lower the frequency. And the more dense the material your string is made of, the lower your frequency. Okay? Finally, what we need to care about. Instead of talking about strict frequencies that strings create, we are going to be going through and finding how changing these variables impacts the frequency of a string. We're going to be doing so by taking a ratio of two things. We have frequency 1 is equal to this, times the square root of t1 divided by L1 d1 root, like this. And then we have the frequency 2 is equal to 1 over the square root of pi times the square root of t2 divided by L2 d2 rho 2. Okay? We're all good with this? When we compare these things, it's easiest to do so as a ratio. Let us divide this by this. Dividing these sides is going to give us some pretty decent benefits. First things first, let's write out what this ends up as. As we can see, the 1 over pi's cancel out. That constant is just a constant. We don't have to worry about it. We're left with here the frequency 1 divided by the frequency 2 on this side of the equal side. On the other side of the equal side, we have the square root of tension 1 divided by the square root of tension 2. Then, note how the length is on the bottom of the fraction up here, and the length is on the bottom of the fraction down here. When we divide these are going to switch places. Length 2 divided by length 1. Same with diameter. We're going to have diameter 2 divided by diameter 1. And finally, what's it called? Density. That's what it's called. We have the square root of density 2 divided by the square root of density 1. And this right here is what we care about. So let's bring this back over to our book and let's copy this down. We have that the frequency. Oh, I'm way up there. We have the ratio of the frequencies of the two strings is going to be equal to the ratio of their lengths divided by each other times the ratio of their tensions divided by each other. Oh, did I screw that up? No, I didn't. I'm great. Never mind. I'm perfect. 2 times the diameters, d2 over d1, times the densities. This right here is the equation we are going to be looking at, as this allows us to directly compare the frequency as the frequency changes due to these different variables being changed. Now, these work in a nice way. Depending on what changes, we can get different sorts of equations out of it. Let's take a look at this right here, this question. We have that a guitar string under 200 newtons of tension plays a pitch of this when it is that long. In other words, the tension 1 of the string is 200 newtons. The frequency 1, the frequency that this string has originally, is 330 hertz. I have to write that somewhere else so that you all can see it. Yeah, there we go. And that the length of the string originally is 74 centimeters. Like that. I'm probably going to turn myself off for this just so we can see this a little better. Okay, cool. Okay. The tension and length are now changed. So there's a change in our situation. Our tension at the end now becomes 325. Our length at the end now becomes 68 centimeters, newtons, and our frequency, we do not know. This is what we are looking for. What is the new pitch of the guitar string? It asks us. Let's look over here at our equation. We are looking for this right here. This is what our goal is. We have this. We know both of our lengths. We know both of our tensions. Note how the diameter of the string does not change from the beginning to the end. Nothing is said about that. Note how the density of the string doesn't change. Nothing is said about that. What that means is that our density 1 is equal to our density 2. Now, I meant diameter 1 is equal to diameter 2. One important thing to do in this equation is make sure you know the difference between density and diameter. I pointed to the wrong ones, density and diameter. D, yes, definitely looks like a density, but it is diameter. Density is the rho that is used in chemistry, so just be aware of that. So our diameter 1 is equal to our diameter 2, and our density 1 is equal to our density 2. What this means is this part of the equation, d2 divided by d1, is going to equal 1. And same with the density. So when we write our equation here, f1 over f2 equal to L2 over L1 times square root of T1 over square root of T2, this part just becomes a 1 times 1. This part just becomes a 1 times 1. So we effectively get rid of those parts of the equation, as nothing changing for them in the situation means we do not have to care about them or account for them in this situation. We can now come over here and actually solve through this. 330 divided by f2 is equal to the original, or the final length, the new length, 68, divided by 74. Note how this is in centimeters, this is in centimeters. When we put the 68 centimeters over the 74 centimeters, these centimeters will cancel. I could change these to meters, but I don't have to in this situation, because since they have the same thing, the ratio will simply eliminate their units for us. Same thing with tension. The square root of 200 newtons divided by the square root of 325 newtons, the square root of newtons on the side of both these cancels out, so we don't end up having to worry about it. This gives us a nice thing, because now we have this. And now that we have this, we can actually solve through this. 330 is equal to 68 divided by 74 times the square root of 200 over the square root of 325 times our frequency 2. So if we can just divide both sides by both of these things, we should be fine. In other words, frequency 2 is equal to 330 divided by 68 divided by 74. I love that. You're just giving it to me in regular form. Oop. Sorry. Let me quickly just modify my stupid calculator so that it is giving me actual values. Okay, cool. Oop. Nope, still not. Thank you. Thank you, calculator. We love you. You know we do. Hello? Huh, okay, cool. So I'll leave it up to you to successfully multiply this across and do it there. I trust you're able to do this. If you are curious, let me just rewrite it in this format that you have, so you can simply plug it in if you would want to. 74 over 68 times square root of 325 divided by the square root of 200. But yeah, okay, cool. So this is this, nothing too crazy, simply calculator stuff that you end up having to do. So keep that in mind. That is going to be one of the main things that we have to care and do stuff about as we move forward. Let's finish talking on standing wave patterns now. Standing wave patterns being one of the few things that we kind of did last time, but we didn't actually finish. So let's just make sure we're all aware of things. We have our standing waves here, here, here. Oh my god, that's not the best, but that's okay. And then 1, 2, 3, doop. 1, 2, 3, doop. Okay, cool. Not the best. I'm not going to be very proud of those, but we're going to keep them for now. Recall that this is the fundamental frequency and the first and second overtones. If we're talking in the harmonic series, this is the first harmonic, and this is the second harmonic, and this is the third harmonic. We didn't really talk about this specifically, but if we were to say, put this as the bass note on a C scale. So if we were to say create a situation, a frequency and a wavelength such that our base note was C on a major scale, well, C has a base frequency of 172 hertz. At least one of the C's does. Just for ease, let's come over here and say that this right here is 1 meter long, or that we have 2 meters of wavelength here, 1 meter of wavelength here. We'll get our frequency here as 344 hertz here. This right here is twice the wavelength, or twice the frequency of our original note. We have to be aware that an octave, whenever we travel up an octave, this is a doubling of our frequency. So what we did just here, double our frequency, means we're moving up an octave. So this creates a note of C at the next octave. When we then go to the next overtone, note how this is 3 times the original frequency, or 2/3, 2/3 of a meter. This is not a doubling of this last frequency, so it is no longer a C note. This now becomes a G note, and those of you who are in music will know the connection between these notes. Let's see what happens when we continue. This one is 4 times the frequency, note so on and so forth for this. This is 4 bubbles, 5 bubbles, so on and so forth. This right here gives us a frequency of 688 hertz, a 1/2 of a meter in terms of thing, and this will give us a C as the 4th harmonic. Note how this makes sense. This is twice this. So we've doubled once for 1 octave. We've doubled twice now for 2 octaves. We're going to have to wait all the way till the 8th harmonic, way down here, before we reach C again, though. As here, we get 5 times the fundamental, or this frequency, for our 5th harmonic, which is a E. And then we get 6 times our base frequency, giving us our 6th harmonic, or the 5th overtone, being G again. Finally, our 7th harmonic, which gives us, I believe, a B flat. Yeah, that looks about right to me. And then finally, we get to this 8th harmonic, or finally another doubling from our last C, giving us our final octave we can talk about here, putting us back at C. So just keep this in mind as how these notes actually fundamentally relate to each other. When we map these all together, you can get simply the overtones of this original frequency. When you play a bass C like this, all of these notes exist within that playing of that note to different extents when you're in the different objects, different instruments that create those. This brings us back to that quality of sound and timbre thing. When we're talking about the timbre of instruments, it's how present those overtones are in those instruments. So when we say have a stringed instrument, it will create this, and then it will create different percentages of these overtones, these other notes on top of it that are constantly interfering with it as it goes. That's different from a trumpet that will have different amounts of these other harmonics, these overtones present in it. That's what changes the quality of sound, the type of sound that different instruments have. And this If you look here, can get a more direct example on that. Oh, I am kind of shitty at drawing, so please forgive me when we do this. Right. All of these things, these overtones, are really just interference patterns of sorts. So if we say have the fundamental frequency that something is putting out, and we have some overtone that looks like this being put out on it, that is at half of that frequency, and a little bit less of an amplitude. When we combine these two things together, it will create an interference pattern. The interference pattern giving a new shape, weird shape perhaps, it doesn't look too good, but hopefully that's fine. It gives it a new shape of sorts, that new shape being the new wavelength that's created for this. Depending on how much of these overtones you get, you modify the original frequency more and more. Note how it's always going to have that same wavelength though, as all of these will always have that sort of wavelength going for them in how they rotate through. So just keep that in mind, as different instruments will have different looks to their things. And this is kind of a bullshit thing, but again, tuning forks and bells will tend to have more pure looking things. Things like a flute might have a more crazy thing, like so. Things like a trumpet might have an even crazier look to them, so on and so forth. So just keep that in mind. Different things will have different looks to them for how they are. We're not really going to talk about this, just same thing about resonance. When you give something its fundamental frequency, it will kind of go bananas for it. And that's all that is. This brings us then to air columns, and I believe we covered this a little bit, but let's just make sure we're all set on it. Let's draw a few air columns for us to do this on, because this is going to be important for us to have. Basically, the different air columns, a closed air column and a open air column, will act with some rules the same between them. Let's draw 4. 1, 2, 3, 4 closed, and let's draw 4 open. Whoop. And whoop, whoop, and whoop, whoop. Okay, cool. So we have our closed and open air columns. Let's talk about how these work. A closed air column, if you think about it, will always be closed on one side. The air on that side cannot move. It cannot compress. It cannot rarefact, because it is in fact a wall. A wall will not compress or rarefact. We can think of this then as a node. This is a place where no movement will occur, because it's a wall. That being said, up here in the open side, well, things can move as much as they want. It is open to the air. What this means is we have a standing wave that has an anode at the top and a node at the bottom, thus creating a wave like this. Note how when we dealt with strings, a string would always have 2 nodes on each side, thus creating a pair of 2 nodes and 1 anode, or 3 nodes and 2 anodes. There always came with 1 more node than there were anodes. In this case, we have the same number of nodes and anodes. When we come over here and make the second order standing wave, here and here, we will have 1 full little bubble here, and then it will open back up here like so. And when we come down here to do it again, we'll have 1, 2 bubbles, and then an anode on the end. Whoop, 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 and whoop, whoop. It will have 2 bubbles and 1 anode on the end. What does this all mean? Well, let's look at it. In these sorts of examples, we will always have an equal number of nodes and anodes. And this means we will always have a bubble that is incomplete. Now, this incomplete bubble is 1/4 of a wavelength. As if we look here, one wavelength is 1 full traversal down and back. If we're only going from here to here, we are only getting 1/4 of that journey. 1, 2, 3, 4. So a half bubble is 1/4 of a wavelength. A full bubble is a full half of a wavelength. The pattern for this closed air tube is the first resonant point has 1/4 of a wavelength of the wave. If we wanted to figure out the wavelength of this wave, we'd have to multiply the length of the pipe by 4 to get it. In this case, we have 3/4 of a wavelength. In this case, 5/4 of a wavelength. And in this case, 7/4 of a wavelength that you use to calculate what that wavelength is. In other words, the length of the pipe is equal to 7/4 of a wavelength in this case. The length of the pipe is equal to 1/4 or whatever, and you can use that to find what your wavelength is. Open air columns are going to work in a slightly different way, right? We have an anode on this side and an anode on this side, thus creating a node somewhere in the middle. Whop, 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 whop. If you note, we have a half bubble and a half bubble, 1/4 of a wavelength and a 1/4 of a wavelength, to give us 1/2 of a wavelength. Hey, wait. Our first thing for a string is also half a wavelength. Note how having 2 nodes and 1 anode is very similar to having 2 anodes and 1 node. And the same thing is going to apply when we have more anodes, but still less nodes. Here like this. Now we are at, again, 1 full wavelength as equal to the thing. And then when we do more, 1, 2, 3, 1, 2, 3, we now have 3 halves of a wavelength. And then when we do it even more, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We have ourselves 4 halves of a wavelength there. So just keep this in mind as we're going through with things. When you're calculating for open and closed air tubes, you can always find the number of wavelengths that they create at whatever resonant point they are. At their first resonant point, it'll be 1/4, 1/2. At their second, it'll be 3/4, 1/2, or 1, so on and so forth. Okay, that is all I am going to leave you with for today. Here are some questions on what we just talked about. I would like you to go through and test yourself on those problems. I will put the answers to said problems right here. The answers aren't anything too crazy. You know, the frequency here is 26.5 hertz. The frequency here is 140 1360 hertz, and then the the wavelength here is 0.786 hertz. Meters, not hertz, meters. And then the length that creates that wavelength is 1.572 meters. So just keep these as your answer key, say, for this. You should be able to go through and get to these answers. Try it out, see what happens. We'll have time and we can chat on this. Otherwise, your homework is as is listed in the agenda and should be listed on the sub slide for today. So try that out, and that should be the rest of class. Thank you all so much.